So that is like a back annotation of delay information of different elements on the chip in a verification environment. And then see, now how does it work? Does it still give me functionally correct data? And does it meet my timing?
So that's done on the device itself, or it's done, still done simulation? But
they still done simulation, but it actually uses a physical, actual device model.
Right, okay, yeah.
And then the last step is your chip level verification, where once you have, which is basically the hardware bring up stage. So once you have the everything connected, at that moment you do again the same thing. But to what extent you do at that moment varies from team to team. Because most of the time, if you are done with your simulation using models, you are more or less sure that it will work on the board.
Go ahead, we're ignorant but interested, so you can ask my questions.
Definitely.
Yeah.
Yeah.
Go ahead.
Now, the other question that I looked at, and these are the only two questions that I've been looking at, is device identification and tracking. So, if you look at medical devices, for an example, the high-end medical devices like pacemakers and defibrillators, everything is tracked. So the moment anything goes wrong, someone has to report it to the parent company, and the parent company has to report it to FDA. So they do this tracking, but their tracking is very manual. It's based on using a database system, and you put every piece of information as a device goes down the chain of the supply chain. So you have this thing of two-factor authentication for authenticating your device on the network. And based on what I have read, is that the two-factor authentication has an issue with scalability. So you can use it with one or two devices, maybe 10, 20, but not when you have thousands of these. But let's say if you have a random string of ones and zeros, which incorporates some information about your device. So how, if say I were to try to crack this piece of information or this string, how many possible, at the least, messages I can generate? So this is that count. Obviously I can have more than this, but this is a very simplistic, crude calculation. And why do we want to do this? Because we want to ensure that there is no device theft, no replacement, and no spoofing. So if you have that string, how can you, can you put information within that string in a way that it still makes sense to you, and it can be generated randomly, or maybe it can change patterns based on certain periodicity, but still have the information that you put in there. So that even if, say, somebody takes this piece of string or bits.
What is that formula there? E times n factorial?
So that's like the sum of, so if it's an n bit number, if there are n bits in a string,
Yes.
and if you take 1 bit at a time, 2 bits at a time, 3 bits at a time, n bits at a time, what is the sum of all of those? So this is just a crude approximation of the different number of messages that you can probably generate, but it depends on other factors. Now I'll just talk about some of the work that people have been doing in this space, which I find interesting, but I have my comments on those. So I have read work where people have looked at the mesh network of an aggregator with smart meters, and it has been said that you can bring down the entire mesh network by just affecting a few nodes. But is this information enough for, say, a utility to act upon it? For a utility to act upon this kind of information, it would also need to know which are the nodes that get affected. And does this information remain constant in time? Or is it like if the network topology changes or the routing protocol changes, this information will also change? So So just saying that I can bring down a mesh network by affecting only a few nodes is not enough. It's not actionable enough for me because I need this additional information to act on this kind of information. And if I get this additional information, I can probably replace these aggregators with secure ones, because I cannot replace all of them, but maybe some of them, because cost is obviously a factor. So this is one thing. The other thing that I have studied here is the attack propagation modeling. Now, if you remember, I have done FTA and FMaker for embedded system designs, which basically look at fault propagation and failure mode and effects, failure modes, their effects, and how critical are those effects in a system. So isn't it very similar to that? Because an attack can be considered as an advanced form of a fault as long as it injects a fault. Now, if this attack is just for stealing information, then maybe there's something else to be done. So if you can represent a smart grid network as a graph and establish this propagation of faults, you can get insight into failures, losses at the bigger industrial scale. Now, why is this a challenge?
At some scale, Sharad, they do the failure modes effects analysis. I mean, it's not uncommon, but it's done at some scale, and it's done within the utilities. And you're right. This is the attack tree and FMEA share this common problem that you can only you can only draw the attack graph for the attacks you know. And similarly, you can only draw the faults really for those faults you know. I mean, that's the basic problem with both.
Yeah.
You know, so, but I think it's the attack graphs are not so popular. Because people do understand that, you know, it's about future. Especially attacks is about the future, not about the past. So it's a good point you make.
And I also see that attack modeling also has challenge because you have different devices from different vendors, and there can be different communication protocols within a smart grid. Now, if you want to do this modeling in real time, you will probably need to have or understand the models of each of those devices and communication protocols. And bringing this all together